Hi, so let's talk about how do we model a solution. So in this unit, we'll talk about how to structure your solutions and how to present them in a very communicable, in a very unambiguous manner. A lot of concepts will be explained and this unit is going to be a little heavy. Let's start with why do we need to model? Why can't we simply communicate? Why can't we simply write stories? Well, that is because communicating effectively and unambiguously is the most important thing that a product manager will ever do. And that's, I would say, that's pretty much the central role that a product manager plays. You see, a business model is an abstract representation of a clearly delimited area of business. It may take many forms: plain text, wireframes, pictures, etc. Many organizations are excellent at developing good software products. Where they are often weak is in developing the right software product. The mismatch between what the user wants and what the developers deliver can often be traced to poor practices in business analysis and quality control. Right modeling provides a step-by-step procedure that helps ensure the completeness, correctness, and clarity of the requirements documentation. In addition, many IT projects experience time and cost overruns due to the difficulty in responding to a rapidly changing business environment. A major contributing factor to this problem is the ripple effect. One change in the business that leads to many changes in project deliverables. So the modeling uh, concepts that we're going to learn in this unit will help us by using object-oriented techniques, which we'll be explaining in a short while, to minimize redundancies in the requirements. With one fact in one place, the requirements are easier to revise. Finally, many project failures are due to the faulty communication between those who know the business and those who write the software. With the modeling techniques that we're going to talk about in this unit, the product manager documents business rules and requirements using the same type of diagrams, concepts, and terminology used by object-oriented developers, thus reducing the risk of miscommunication. So broadly, when you model a certain software project or any project for that matter, you can divide them into two parts: behavior model or structural model. You can also call it dynamic model or the static model. The dynamic model tries to answer what does the system do. It is verb oriented. It tries to judge or analyze the system by its actions. That is, it tries to understand that what the system is doing. Okay, and you would use diagrams like use case diagrams, decision trees, activity diagrams, and so on. If you don't know these diagrams, don't worry, we'll be covering them very soon. And the other one is structural model or the static model, which tries to answer what is the system. It is noun oriented and it will try to understand what exactly is the system composed of. Right? So for example, if you take an example of a car, uh, the static model of the car talks about the steering wheel, the engine, the chassis, the color, and so on, while the dynamic model will talk about the torque, the speed, the peak speed, and so on. Right? The other important thing that you, before we jump into before we deep dive into the entire modeling discussion, remember these three terms: elegance, adaptability, and non-redundancy. When you will be modeling any product, make sure that these three parameters or these three factors are taken care of. A simple solution to a complex problem. Typically, when you get that moment, when you get that simple solution to a complex problem, you'll get that aha feeling that, oh yeah, this is so better than what we have been using so far. Adaptability. So the solution can easily be changed to reflect a change in the requirements. So if the things change, the product can be moved, can be changed. And finally, non-redundancy, which is one fact in one place. So do not repeat itself. That's a good modeling. These are the three um, great qualities of a good modeling decision. Let's talk about, before we deep dive into modeling, let's talk about object orientation. And I'll take this moment also to explain why are we learning about modeling as such. We're learning about modeling is because a common term that is that you might have heard is PRD, product requirements document. Effectively, at the core of it, product requirements document is nothing but modeling a certain solution, where you exactly describe how a particular system should work, what conditions should be met, and when it should be met, by whom it should be met, and so on. Right? So instead of talking about PRD, because that's like the manifestation of the code, uh, the core skill of modeling, I'm talking about modeling here. Once you understand modeling, you will be very easy to actually write a good PRD. So let's talk about object orientation. For those who are developers, you might have heard of this term, object orientation, or object oriented programming. So we are going to, in this subtopic, we are going to talk about object oriented, right? So what is OO? You will see this OO a lot of times. So OO stands for object oriented or object orientation. Object oriented system consists of a set of objects that collaborate by sending requests to each other. Okay. So conceptual framework that it affects the way PM analyzes and models the requirements. That is why we are learning about this. The software engineer designs the system specification. So a lot of programming language, in fact almost all the programming languages which are in use today, they have object oriented fundamentals. And that is why, as a PM, if you understand this as well, it will make your life very very easy, because you will be able to communicate in the same language that the software engineer understands. And finally, the way the code itself is structured is also object oriented nowadays. Okay. So to give an idea, just look at the diagram that follows, right? So there is vehicle, and then there's wheeled vehicle, and then there are non-wheeled vehicles. In non-wheeled vehicles, there's an example of a boat, right? They could very well be a rocket, for example. In wheeled vehicle, then you have, in this diagram we just explained two wheelers and four wheelers, but there could be one wheeler, there could be two wheeler, there could be three wheeler, there could be four wheeler, there could be so many others one, right? But you can imagine the entire hierarchy coming along, right? So as a product manager, your job is to get inside the heads of your stakeholders so that you can extract what they know about a piece of the real world, that is a business system, and pass it on to the developers who will simulate that system on a computer. If you were choosing an approach for doing all this, you would want something that goes as directly as possible from the stakeholder's head to the final solution. This approach would have to begin with an understanding of how people actually think about the world, and would have to be broad enough to take the project from requirements gathering right through the construction of the software. Object orientation is one such approach. It begins by proposing that the object is the basic unit by which we organize the knowledge, right? So in this case, you can talk about, let's say, the smallest vehicle or the smallest moving object, and then you build the soft system around it. In the following discussion, we will see how object oriented takes this simple idea, uh, that there's a basic object, there's a basic unit which is the object in a particular scenario, and around that we can organize the entire knowledge, just like atoms and molecules, something similar here, right? So we'll be learning very soon that this simple idea of object orientation, and we'll build an entire edifice of powerful concepts that can be used to understand and build complex systems. So object oriented begins with the observation that when you perceive the world, you don't just take it in as a blur of sensations. Rather, you distinguish individual objects, and you have internal images of them that you can see in your mind's eye, right? So when I say car, you have an imagination, right? There is a car in your head. Now you might be thinking of Jaguar, I might be thinking of Mercedes, whatever that is, but at least we both are thinking of cars. Taken together, these internal objects model a segment of the real world. So you begin to analyze a business area by asking stakeholders to describe the business objects it encompasses. Let this sink in, right? You begin by asking stakeholders. The stakeholders could be your business people in the internal in the company itself, or your customers, your potential users, and so on. So you ask them to describe the business objects it encompasses. For example, if you're designing a new age invoicing tool, you'll perhaps talk to your sales team to understand how a particular invoice flows through the system. When is it raised? By whom is it raised? What are the steps through which it goes through? Who are the people who touch that invoice? And what are the um, gating conditions for the invoice to pass through the individual stages, right? So, effectively, you can model the entire system around an invoice. That's it, just an invoice. So, invoice becomes the object of the entire product, correct? So a business object is something the business and the IT system that automates it must uh, keep track of, or that participates in business processes. So example, in our case, uh, invoice is an object, right? So so keep this in mind that uh, when you're interacting on it, when you're trying to model a system, look for the business objects which needs to be modeled. Typically, these would be the ones which must be tracked or it participates in business processes. Example, invoice, call, credit note, user, in a Facebook, in Facebook's case, for example, a single post, that's an object. The second concept that you need to understand about object oriented is attributes and operations. So we learned about objects, now let's understand attributes and operations. So object oriented theory continues by examining this kind of the kind of knowledge that is attached to each internal object. So we defined a object, let's say invoice. So what is the additional knowledge that we have about this object invoice? Because we can recognize an object again after having seen it once, our internal representation of an object must include a record of its properties. For example, we remember that a shirt object's color is blue and its size is large. In object oriented, color and size are referred to as attributes. Blue and large are attribute values. Every object has its own set of attribute values. Something else we remember about an object is its function. For example, the first time you saw a crayon, it took you some time to learn that it could be used to scribble on the walls. Unfortunately for your parents, the next time you saw that crayon, you knew exactly what to do with it. Why? Because you remembered that scribble was something you could do with that object. In object oriented, scribble is referred to as an operation. To sum up what we have established so far, two things we remember about objects are the value of their attributes, that is the color, the shape, the size, and so on, and the operations that we can do with them. We can drive it, we can issue it, and so on. The next step in analyzing a business system is to find out what attributes and business operations apply to each object. Take this in mind. So once you've identified the objects in your business system, next is you need to identify what attributes and business operations apply to each object. For example, two attributes that apply to an account object are balance and date last accessed. Correct? An account in a bank, if that is an object, then there are two things that we would like to know. One, the balance, and the date last accessed. Correct? So these two things are the attributes. And two operations that relate to the object of account as an object are deposit and withdraw. An object's operations usually change or query the value of its attributes. So when you operate on that object, it will typically change or it will query the values of its attributes. For example, the withdraw operation changes the value of the object's balance attribute. But this is not always the case. For example, view transaction history, another which is another operation that applies to the account object. displays information about all the transaction objects tied to the account. However, it might not refer to any of the account's attributes. I hope this is clear, right? So attributes and operations. Uh, in the example that I've shared here, in the animal, when I refer to an animal, you can come up with dog, you can come up with sheep. Now, dog is yellow in this particular case, which is an attribute. So, which is the color? What is the color of the animal? So that is an attribute. And what are the operations that this object can do or we can do on it? So this particular dog is a smart dog, so he can ride and he can run, right? And there is a sheep which is white in color and it can run, although it can run faster than dog, but yeah, right? So this is the second concept that you need to understand. So attributes, they represent the properties of objects and store the values, and operations represents what we can do with the objects. Let me go slightly deeper into operations and methods. Okay, so going one step further, you don't just remember what you can do with an object, you also remember how you do it. For example, you know that you can place a call with a particular mobile phone, but you also remember that to do so, you must follow a particular procedure. First, you enter the phone number and then you press the send key. In object oriented terms, place a call is an operation. The procedures used to carry it out is called a method. I'll just repeat this. In object-oriented terms, place a call is an operation. The procedure used to carry it out is called a method. So next, you take each operation and ask stakeholders what procedure they use to carry it out. You document the procedure as a method. For example, you ask stakeholders what procedure they follow when withdrawing funds from an account. They tell you that they first check to see if there is a hold on the account and whether there are sufficient funds available for withdrawal. If everything is in order, they reduce the balance and create an audit trail of the transaction. You document this procedure as the method used to carry out the withdraw operation. So withdraw is an operation and this entire sequence of steps becomes a method, right? So for example, in this case of a car and a dog, so if dog is the object, there are property values of color being gray, white and black, eye color being blue and brown. These are all attributes. While there's a method of sit, lay down, shake, and come, these are all different methods that you can you know that this dog can operate upon in order to complete an operation. Correct. Similarly, in the car scenario, their attributes are fuel, the max speed, and all. While the methods are refuel, get fuel, set speed, get speed, drive. Correct. These are all methods that you can do. This is how you can operate on the car. Next concept that we want to talk about is encapsulation. This is a very powerful concept and something that you need to understand really well because this improves the modeling uh, a lot. So every day you use objects without knowing how they work or what their internal structure is. This is a useful aspect of the way we humans interact with other objects. It keeps us from having to know too much. It also means that we can easily switch to another object with a different internal structure as long as it behaves the same way externally. Correct? So, for example, as humans, we keep interacting with each other. We don't know what's going on in each other's head. How stressful is your professional life? How stressful is your personal life? Are you actually happy? Are you not happy? But externally, in a business environment, in the office, or in a certain setup, we all interact in a certain fashion. Why? Because we have encapsulated all our feelings, all our emotions, all the internal whatever is going on, because we want to facilitate a certain sort of interactions in a setup, in an office setup. Similarly, in the when you're using a laptop or a mobile phone, as long as externally everything is okay, that is, you are using the same that you know how to dial a phone call, how to write an email, and so on. It doesn't matter when how exactly internally things have changed, with the chipset has changed, or the screen has changed, or whatever. Correct. So this concept, this object oriented principle, is called principle of encapsulation, or simply encapsulation. So only an object's operations are visible to the other objects. Attributes and methods remain hidden from view, unless obviously it's an external attribute. So the methods are the internal procedures used to deliver that operation, or used to conduct that operation. Correct. So the method is hidden, the attributes are hidden, only the operations are visible to the other objects. So when you describe the method of an object, don't mention the attributes of another object or presume to know how another object performs its operations. The benefit to this approach is that if the methods or attributes related to a business object ever change, you will have to make corrections to only one part of the model. I hope this is clear, right? So only objects' operations are visible to other objects, nothing else is visible. Attributes and methods remain hidden from the view, right? So in this case, for example, in the camera's case, there's a lot of mechanism happening in the backstage, right? But everything has been abstracted out to just 3 or 4 operations: how to zoom in, how to zoom out, how to switch on the flash, how to switch off the flash, how to autofocus, and how to take a photo. That's it. You are not bothered about knowing how exactly things work, what happens when you click on zoom, what happens when you click on autofocus, what are the internal mechanisms that are happening. Correct. But as you can imagine, internally there are a lot of methods that get into action as soon as you click on autofocus. The next concept that we need to understand is classes. Okay. So you have seen that our ability to internally model an object allows us to use it the next time we encounter it without relearning it. This does not automatically mean, however, that we can apply what we have learned to other objects of the same type. Yet we do this all the time. For example, once you have learned how to use iPhone X or iPhone 10 for the Apple purists, we know how to use all iPhone 10 objects. We can do this because we recognize that all these objects belong to the same type, iPhone 10. In object oriented, the category that an object belongs to is called its class. Okay, so a very simple example would be the cars diagram that you can see. There's a class called car. Now within that class there are multiple objects. There's a green Ford Mustang which runs on gasoline, there is a red Toyota Prius which runs on electricity, and there's a blue Volkswagen Golf which runs on diesel, with the wrong spelling. um, so the minute you know that two objects belong to the same class, there is a car for example, you know a number of things about them. Correct. The same attributes apply to both the objects. For example, you know that both objects will have a serial number. In the case of a phone number and various camera settings. Each object will have its own values for these attributes. The same operation applies to both objects. For example, you can place a call and take a picture with each of these objects. The same methods apply. For example, the procedure for placing a call is same for both the phones. Right? To summarize, a class is a category. All objects that belong to the same category have the same attributes and operations, but the value of the attributes may change from object to object. Despite the name object oriented analysis, you will be spending most of your time defining classes and not objects. Remember that, okay? So, it's object oriented, but effectively you'll be working at the molecule level. To give you another analogy, you'll be working on the molecule level instead of the atom level most of the time. Right? So the classes you will be interested in are those that relate to the business. These are termed entity classes. For example, in a banking system, you would define the characteristics of an account entity class and a customer entity class, right? Let's move on. The next important concept in object oriented is relationships. Okay, so we often define one class in terms of another class. Once we have defined all these individual molecules, we also need to understand how these molecules relate to each other. Do they react with each other? They don't react with each other? Is one molecule part of another molecule, right? So for example, a car is a kind of a vehicle. Both car and vehicles are classes. The phrase a kind of describes a relationship between the two classes. The UML defines a number of types of relationship that are useful to the PM: generalization, association, aggregation, and composite aggregation. Okay, we'll go through each one of them one by one. But I just mentioned a term called UML. Well, UML is full the short form for Unified Modeling Language. This originated somewhere in 70s, if I'm not wrong, and it was an attempt to have a very clean, very unambiguous modeling language using which we can describe how the software should be modeled and should be built. It went on to that level that if you can model using diagrams and everything properly in a scientific manner, then you can generate a workable code just using these diagrams, right? UML is still in use, but it is not so much in use amongst the startups and amongst the tech companies because it does take a little bit extra time. Uh, and so, in what I've done is, but I strongly believe in the values of what UML brings. In fact, a lot of the artifacts that we use today to model our systems or that we use in PRDs like flow diagrams and so on, they're effectively they're actually UML artifacts, just that people don't know about it. And honestly, you don't need to know about UML in depth because UML is very huge. But what I've done is I have gone through I have abstracted out the few uh, diagrams and few concepts that matter to you and which we'll be covering in the coming units. So let's move along. Let's talk about generalization. The concept of a class allows us to make statements about a set of objects that we treat exactly the same way. But sometimes we run into objects that are only partially alike. For example, we may own a store that has a number of iPhone 10 objects and a number of Samsung S8 Plus phone objects. The iPhone 10s are not exactly like the Samsung S8 Plus phones, but they do share some characteristics. For example, the ability to place a mobile call. We treat this situation by thinking of these objects not only as the iPhone 10 or Samsung S8 Plus phones, but also as mobile phones. A particular phone object, for example, might be able to run a particular iPhone application by virtue of being an iPhone 10, but it can also place a mobile call by virtue of being a mobile phone. Correct? So in object oriented, mobile phone is referred to as the generalized class. iPhone 10 and Samsung S8 Plus are referred to as its specialized classes. The relationship between the mobile phone class and either of its subtypes, that is iPhone 10 or Samsung S8 Plus, is called generalization, right? So for example, if you look at the scissor photo, you can without even explaining to you, you can easily see that all of them are scissors, right? But how do you know that these are all scissors? Because they all have the similar function or the same operation. They cut, right? And they have a place to hold this instrument, correct? So that is why scissor becomes a generalized class to represent these four scissors, and each of them are independent scissors or objects, or you can also call them a specialized class. right? So the process of generalization is to convert the many perceptions about a particular object towards one idea, that okay, all of these objects or all of these classes would act in a certain way, and that becomes a generalized class. So why do we generalize? Well, we do that because it allows us to make statements that cover a broad range of objects. For example, when we say that a mobile phone can receive a text message, we are stating to a rule that applies to all of its specializations. When an object belongs to a specialized class, for example iPhone 10, this automatically implies that it belongs to a generalization of that class. For example, mobile phone. Any attribute or operation that applies to the generalized class also applies to the specialized class, right? Furthermore, any relationships specified for the generalized class also apply to the specialized class. For example, the relationship customer owns one or more accounts in a banking scenario. Customer owns one or more accounts. Those specified for the account class applies also to checking account, savings account, correct? So the checking out account as well as savings account and all other account types, correct? So so by generalizing, it just helps in keeping things absolutely clear at uh, the operation level and at the attribute level. What are some of the other terms that are used? Um, well, generalized class, specialized class is one. Superclass, subclass is also used. Base class, derived class is also used to mention the same thing. Parent and child is also used to mention the same thing. The idea that a specialized class automatically adopts the attributes and relationships of its generalized class is given a special name in object oriented concepts, and that is called inheritance. Okay, so specialized class inherits the attributes and operations and relationships of its generalized class, right? So in this case, for example, the scissors, the four scissors, they have inherited the attributes, the operations and the relationship of a generalized class of a scissor. So how do you apply it in your real world scenarios? Well, you look for classes of business objects that are subtypes of a more general type. Okay, so for example, the checking account and savings account are two kinds of accounts, right? As soon as you say this, there are two kinds of accounts. So actually, be very careful or be very observant about the kind of words that you're using, because that itself will kind of tell you um which relationship this could be. For instance, checking account and savings account are two kinds of accounts, which basically means accounts seems to be the generalized class, and two kinds basically indicates that savings and checkings and checking account seems to be the specialized classes. Then you document which attributes and operations apply to all accounts. That is, which which apply to all the accounts and which apply only to the checking account and only to the savings account. Okay. So once you have defined the attributes and operations on each of these classes, that is the checking and the savings and the general accounts, you can actually see which rules or which attributes or which operations are common for the three. Correct. For accounts, that is a broader generalized class, checking account and savings account, right? So once you do this, once you structure this, then you just have to document it once, right? And then that also makes it easier to revise the documentation if these business rules ever change. It also gives you the opportunity to state rules about accounts that must apply to all future account types, right? Even one you don't know about yet. And that is the power of modeling properly. That as things evolve, as the new products and new requirements and new situations arise, you are not scrambling to fix and change everything internally again and again. If you model it correctly, uh, then a lot of the rules, a lot of the things that you have set up right now with the current accounts, with the current operations, with the current classes and the relationship between them, They will also apply for all the future accounts, and that makes life very, very easy. Next, let's talk about association. So another way that classes may be related to each other is through association. When you connect a mouse to a PC, you are associating mouse with the PC. An association between two classes indicate that objects, that is instances of one class, may be related to objects of the other class. Okay, so you specify an association at the class level, you specify a link at the object level. Okay, so how do you apply it? Well, you analyze how the business links objects of one class with those of another for some time, or sometimes with other objects of the same class. So this association can happen between objects of two different classes or within the same class. So for example, the military needs to track which mechanics serviced each piece of equipment, what the maintenance schedules is for each one, and so on. As a PM, you document these type of rules as associations. This is a critical part of your job, and misassociation or documented incorrectly, and you may end up with software that does not support an important business rule. Right? To give you an idea, um, um, just look at the example here, right? So the personal computer has a mouse, has a keyboard, has a monitor, contains a system unit, or a better thing would be, there's a personal computer is associated with mouse as a signal input device, as a character input device, as an output device. So there's also so this example indicates two things. One is the good names, that how exactly you should be naming them, and what kind of relationship you want to, how do you want to create, how do you want to name the association between these two classes, and also how classes in general, associations in general work. Now let's talk about aggregation. So aggregation is the relationship between a whole and its parts. For example, an insurance policy is an aggregation of a basic policy and amendments to the policy, and a stamp collection is an aggregation of stamps, right? Formally in the UML, aggregation is considered to be a specific type of association. Okay, so typically aggregation is not given a separate stand, but then again, because it's so common and it's so important, that in a lot of discussions it's given a separate place of its own, right? But in the technically in UML, aggregation is considered to be a specific type of association. Okay, that is a connection between or relationship between an object of a particular class to another object, right? So it's a specific type of association as per UML, where the class on one end of the association represents a whole and the class at the other end represents a part. Aggregation may be used by the PM as an alternative to modeling an association with the name is a part of. So whenever you are describing two objects or relationship between two objects uh, with a phrase is a part of, X is a part of Y, you would typically be dealing with aggregation. So how do you apply it? You look for business objects that are made of other business objects. So you model these relationships as aggregations. Then you focus on which rules, that is attributes, operations and relationships, apply to the whole and to which apply to the parts. One thing this process enables you to do is reuse the requirements of a part object in a new context. So let me explain. For example, you model an ATM card as an aggregate, one of whose parts is a pin. You define the attributes and operations of a pin. Later, you reuse the pin requirements for a credit card system that also uses pins, right? So for example, composition is every car has an engine, and aggregation is cars may have passengers, they come and go, right? I just want to clarify the difference between composition and aggregation here. So aggregation is basically uh, when a certain class can be called as a part of another class. right? And composition also deals with something similar, but the difference is composition, every car has an engine, while aggregation is little decoupled, just like ATM cards. ATM cards have pins, but then again sometimes ATM cards will not have pins, or certain cards do not require pins, right? So aggregation basically means the passengers can come and go, while composition, every car has to have an engine, only then the car will be complete, right? And what is the difference between composition versus inheritance? I will leave that to you guys. The next concept is composite aggregation, which we were just discussing in the previous slide. So composite aggregation, also known as composition, is a special form of aggregation wherein each part may belong to only one whole at a time. So formally, composition is a specific kind of aggregation. In aggregation, a part may belong to more than one whole at the same time. In composite aggregation, however, the object may belong to only one whole at a time. The parts are destroyed whenever the whole is destroyed, except for those parts that have been removed prior to the deletion of the whole. Formally, composition is a specific type of aggregation, right? Just remember that. What if you are not sure what kind of whole part relationship to use, right? Because I just spoke about composition, I spoke about aggregation, I also spoke about association, and I also said that these three are a special kind of associations effectively. Well, to be very honest, just don't be too worried about, if you're not able to decide whether a particular whole part relationship is best described as an aggregation or composite aggregation or something else, right? While the distinction from a product manager perspective is helpful, it is not critical, okay? So if you have any problem deciding, specify the whole part relationship as an aggregation. If you're not even sure whether the relationship is best described as a whole, as a whole part relationship, then just model it as an association and just move along, okay? In the course of modeling, you will perhaps come up with you will be able to figure out whether you want to go deeper from association to aggregation or not, but if you're not able to figure it out, it's perfectly okay. So between aggregation and composite aggregation, if you're not able to figure out, just use aggregation. If you're not able to figure out whether this is actually an aggregation or should I model it as an aggregation or not, then just call it an association and just move along. Because you see, like everything, the entire modeling exercise is also iterative. So you'll start with something, you'll go along and you realize, no, I'll actually benefit if I just remove this one component and model this separately, because I'll be reusing this particular component again and again, right? In which case it makes sense to just go back and change the relationship, right? So in fact, very simply, there's nothing wrong with the product manager modeling all whole part relationships as simple associations and not using aggregation at all, right? So you lose a little bit of nuance in the model, but it still will make no difference in the resulting solution, okay? So how do you apply it? So you model strong whole part relationships between classes of business objects as composite aggregation, right? For example, in an analyzing an ERP, which is enterprise resource planning system, for a diamond trader, I modeled a diamond case report form as a composite aggregation of modules. The case report form was a record of everything that was recorded about a diamond with respect to the trade being conducted. That is, somebody was buying the diamond and somebody was selling the diamond. So each module was a record of one interaction with the diamond. The developers understood from this model that each module could only belong to one case report form at a time, and that when a case report form was removed from the system, all of its modules need to be removed as well. Let's talk about another very important concept, which is polymorphism. So polymorphism means the ability to take on many forms. The term is applied both to objects and to operations. So polymorphic objects, let's talk about them. So suppose a financial company handles different subtypes of funds such as an Asia fund, domestic fund and so on. each with its own idiosyncrasies. The PM models the situation using a generalized class, fund. You can see, right? There's a generalized class called fund, and then there is a subtype of and a specialized class called Asia fund and domestic fund. Next, the PM moves on to capture investment rules in an investment class. Checking with the stakeholders, the PM finds that one of its operations, invest capital, deals with all funds the same way, regardless of subtype. The PM handles this by ensuring that the documentation for the invest capital operation, which you can see here, refers exclusively to the generalized class fund, not to any of its specializations. So when the operation is actually executed though, the fund object will take on one of many forms. For example, an Asia fund or a domestic fund. In other fund, the fund object is polymorphic. So when the operation is in place, the fund will take the shape of Asia fund or domestic fund. But otherwise, in all the documentation of invest capital, you will only talk about fund as a generalized class. The next thing is polymorphic operations. So continuing with the same example, since all the fund subtypes have to be able to accept deposits, the PM defines a fund operation called accept deposit. This operation is inherited by all the specializations, right? Because there's generalized class and there's a specialized class. But what if one or more of the specializations, for example, the Asia fund, uses a different procedure for accepting deposits? In this case, the PM can add documentation to the Asia fund class that describes a method that overrides the one inherited from the generalized class. For example, the method described might involve supplementary charges. In practice, when capital investment causes a fund to perform an accept deposit operation, the method that is used to carry out the operation will take on one of many forms, which is what is meant by a polymorphic operation. With polymorphic operations, the selection of the method depends on which particular class, that is the Asia fund, domestic fund, and so on, is carrying it out. Okay. So how do you apply it? Well, when you define operations for a generalized class, in this example it was fund, you look for those that all specializations must be able to support. If you can, you define a method that describes how the operation is typically carried out. If any specialized classes have different ways of doing the operation, you define a new method for it at the specialized class level. Okay, I'll just repeat this. If any specialized classes have different ways of doing the operation, you define a new method for it at the specialized class levels. For example, if you want the Asia fund to operate in a separate way, in a different way as compared to what has been defined at the fund level, then you define a separate document. You create a separate operating process, correct? And you will define that as a new method at the specialized class level itself, right? So this simplifies the documentation, right? You don't need to write if the type is X, then do one method. If it is Y, do another one. Instead, you get this across by where you document the method in the model, right? So in a nutshell, polymorphism is basically one interface, many implementations. So polymorphism enables you to think of all the interactions in as one interface, while the implementation will vary depending on what exactly is happening or which objects or classes are involved. Cars, for example, are designed with polymorphism in mind. They all use the same interface, an accelerate paddle to change speed, even though the internal method may differ from model to model. The auto industry designs cars this way so that drivers do not have to learn a new interface for each new model of car. Correct? So let's move along. The next important concept that we need to understand is use cases and scenarios. Don't get scared about this diagram right now. It's relatively simple. When you start actually doing it, you'll understand it very easily. So a scenario is one path through a use case. One way that it might play out. I've seen too many product managers making this mistake of not having the right definitions in mind. So keep the definition of scenario or when to use what very very clear in your head, so that will make your life much easier when you actually go about describing all the situations. So a scenario is one path through a use case. You want to go from point A to point B. There are multiple routes to get there, right? So that is the scenario. So scenario one is you're going taking a shortest route. Scenario two is you're taking the longest route. Scenario three, you are taking the scenic route. Scenario four, you're taking the bike route, and so on. But all of them correspond to the same use case of moving from point A to point B. So to give an example of the use case, some of the use cases that customers need in a web-based banking system are make bill payment, stop payment, and order checks. And to give an example of scenarios, the make bills payment use case may play out in one of the following ways. Scenario 1, attempt to make a payment from an account and succeed in doing so. Scenario 2, attempt to make a payment from an account and fail because there is a hold on the account. These are both the scenarios, correct? During behavioral analysis, you identify and document the use cases of the system, what the users want to do with it. Okay, what they are saying is attitudinal. What the user is saying is more attitudinal, that this is what I would like to do and things like that. But what they actually use and how exactly they are using system defines the behavioral traits of the customer. And you do this by identifying and describing its scenarios, all the ways the interaction could play out. These use cases and scenarios are your user requirements. Okay, so all the prior discussions about objects, classes, generalized classes, this and that, all of them essentially boil down to this one particular thing, which was these use cases and scenarios are your user requirements. To gather this, you need to be able to talk to your customers and users in their own language and observe how they are behaving, how they are using the product or the system, which will help you in identifying which are the scenarios in which they're using it, which scenarios are good, which scenarios are bad, which scenarios you want to incentivize, which scenarios you want to kill, and then that will help you in creating the use cases which you need to support, right? So in the diagram that you're seeing is a use case diagram. Okay, and this in this use case diagram you have reached a hotel or restaurant, and you have it basically describes the entire process of ordering food and receiving the food, right? It's a pretty interesting one, and it actually explains you how the different scenarios can play out, what are the different relationships between the entities involved. So there's a cashier, there's a waiter, there's a chef, and there's a patron, right? It's very interesting. Have a look. Let's go slightly uh, deeper with the use cases and scenarios, because it's very very important, right? So use cases refers to an interaction with any type of system. The question is, what type of system is being referred to? So business use cases are interaction with the business system. For example, process claim is a business use case describing an interaction with an insurance company, while the system use case is an interaction with an IT system. For example, system use cases that support the aforementioned business use case, which is the process claim, the system use cases that connect to that are record claim, validate coverage, assign the adjuster, and so on. Each of these describes an interaction between a user and the computer system. A system use case typically involves one active primary user, that is typically a human, and takes place over a single session on the computer. At the end of the system use case, the user should feel that he or she has achieved a useful goal, right? And system use cases are often called just use cases. Okay, so take some time in just sinking in and accepting and understanding the use cases and scenarios, and how it connects to processes, how it connects to classes and objects. So how do you apply this entire learning? You will typically draw something called activity diagram to describe use cases and scenarios. Okay. System use cases drive the whole dev process. Okay. So for example, in each release, a planned set of system use cases is analyzed, unless this was done upfront, designed, coded, and implemented. With this use case centered approach, users get features that add real value to their jobs with each software release, right? So in this case, for example, the use cases are how do you apply it? The flow is very simple. You identify the business use cases. That is, you focus on the business aspects of proposed changes or proposed improvements. You look for activities that the product will cover. So you analyze the business use cases and you identify which activities do you want the product to support. Then you group the activities into system use cases. That is, ensure that each system use case gives the user something of real benefit. This manifests itself in the form of features and releases, right? And then finally, system use cases drive the whole dev process. For example, in each release, a planned set of system use cases is analyzed, designed, coded, and implemented, right? And with this use case centered approach, you are able to produce features which finally the users are finding it users find valuable, and they would like to pay for it. I hope this is super clear. So to conclude, we have we went from the baseline, which is objects, how objects work, the relationships, the associations, the classes, and finally how all of this culminates into use cases and scenarios. As a product manager, this is all that you need to care about. This object oriented is a separate course in itself, but this is something which I've abstracted out for you, that this is all the stuff that you need to care about and you need to understand, but internalize it. I will strongly recommend that you internalize it. You spend some time understanding these terms. Maybe uh, uh, do some internet research and learn a little more examples. Take look at some more examples and observe the things around you and try to find out the relationships and associations and start thinking in terms of objects and relationships, because this will help you a lot. Thank you. That's all for now. Take care.